All right, hello everyone. Welcome to the 9th lecture of the quarter in Physics 7C, and I think I will try to conclude all the material that you will need this quarter. So next week we will focus on reviewing the quarter. All right, so what we have left to do is kind of wrap up electromagnetism. So what have we, to be able to move this screen a little bit so I can, okay, so what have we covered so far? Well, we have discussed electric fields, and we saw that they're generated when there are electric charges present. So electric charges are sources for electric fields. Then if you have another electric charge which is somewhere in the presence of an electric field, that charge will feel a force. So that kind of described our electric forces. Now, then we went on to talking about magnetic fields. And although at first, kind of from our daily experience, we think of them as very separate things, so it turns out that they're the source of these two fields, electrics and magnetic, are both due to electric charges. So magnetic fields are created by the motion of these electric charges. So we saw, for example, when there was a wire in which current was flowing, that resulted in a magnetic field. Now, a moving electric charge in a magnetic field, so when your charge is the one that's the test, and what's in the presence of that magnetic field, which is generated by some other moving charges, that moving charge will feel a force. So we call that Lorentz force. And then what we're going to look at today is this kind of last concept, and the fact that a changing magnetic field, so here when we have already a charge which is moving in a magnetic field, it will feel a force. But this is related to this phenomena that when the magnetic, so if your charge, let's say, is stationary initially, but if we introduce a changing magnetic field at the location of the charge, that will cause that charge to move. So this is known as magnetic induction, because it's magnetism or magnetic fields, specifically changing magnetic fields that induce charges to move, or in other words, induce electric currents. And then we'll kind of wrap this up in a generalization of what exactly is electromagnetism, or specifically what are electromagnetic waves, why they call that. So that's what we'll see at the end of this lecture. All right, so this is just a summary of last week. We looked at these two right-hand rules, which told us about, so the first right-hand rule tells us about the direction of the magnetic field due to current. So when you have charges that are moving, in this case you have current going up, you use this first right-hand rule where you put your thumb in the direction of the current, and how your fingers curl define the direction of the magnetic field. Now the magnitude of that is given by this equation, so it's proportional to the current and inversely proportional from the distance away from that wire. Now the second right-hand rule has to do with the Lorentz force, and that has to do with charges that are moving, feeling a force in the presence of an external magnetic field. And we use, so some of your TAs might have taught you the three-finger one. Here's the palm one, where you put velocity in the direction of the speed, your fingers point in the direction of a magnetic field, and your palm is kind of pushing in the direction of the force. And here's the equation that tells you about the magnitude of the force. Again, the right-hand rule you use to get directions, in both cases, and these equations you get to use to figure out, in this case, how large is the magnetic field. Here's how large is the force. So it depends on that charge. So really this has to be a positive value of that charge, you know, whether it's minus 2 coulombs or plus 2 coulombs, you put 2 coulombs here, because that's the magnitude. How fast the charge is going, how strong is the magnetic field, and then that angle between the, here it's actually written with a different letter. It should be theta to be consistent with this equation, but it's the angle between V and B. All right, so now we're gonna move to this idea of induction. So the scientist that first came up with this is Michael Faraday back in the 18th century. And what he observed is that a changing magnetic field through a wire loop, so if you have a loop of a wire, that changing magnetic field would induce an electric current in that loop. So unfortunately, because I'm doing this lecture from home, I don't have really fun demos to show you, but in the actual lecture hall, there's a lot of fun experiments you could do. Literally just move a magnet through a loop of wire attached to, let's say, a light bulb, and you can actually watch that light bulb turn on. No batteries, no power source. So kind of really demonstrating this idea of magnetic field, which is changing, causing current. All right, but before we get into kind of describing that mathematically, we need to introduce this new idea of flux, because the way this magnetic induction is most easily described mathematically is not thinking about changing magnetic field directly, but thinking about flux. And flux, you could think of flux as kind of like the density of magnetic field. So if you take some given area, and we're going to be talking about mostly loops or wires. So if you've taken an area like this, you can think about the flux as sort of the number of field lines that are going through this area. So you could already kind of see, well, let's say the magnetic field. So here we have magnetic field lines going through here. So let's say that the magnetic field was stronger than the one presented here. How do we depict stronger? Stronger means that the density of field lines is greater. So you would have more field lines going through here, larger flux. Also, if you had a larger area, so if you kept the field lines the same density, so the magnetic field strength is the same, but if you increase the area, that would also increase the flux. So to kind of, again, mathematically describe this, what's important, an important kind of variable to introduce here is what is known as the surface normal. So it's a vector that points perpendicular to your surface. Because what's going to matter is not only how many field lines are going through your area, but also the relative orientation of your area to this magnetic field. Okay, so in 3D space, a two-dimensional surface is uniquely defined by that perpendicular direction. So that's how you define this is my surface, by not only saying, okay, this is its area, but also which way is it oriented relative to some axis that you define. And it's that vector that tells you about the orientation. So you can kind of think of this as an area, which is a vector. So that's known as a surface normal. So how would we maximize the amount of flux? Well, if the surface normal is parallel to the magnetic field lines, this is how you get the most field lines, the greatest flux going through your area. So, and then you could kind of visualize as you start rotating this area relative to this field lines, there would be less and less that would actually go through the area. So think about an umbrella. How do you maximize the number of raindrops that your umbrella will get? By holding it straight up so the rain is hitting it perpendicular. If you were to rotate the umbrella in the direction of the rain, there's less and less rain that hits it, although the rain itself, let's say, didn't change intensity. So this is the orientation that results in maximum amount of flux. when the surface normal is parallel to the magnetic field. Now, what's the minimum amount of flux you have? Well, if the surface normal is perpendicular to the field line, so if let's say the field is coming from above straight down, there's no field lines that are actually going through this area. So this is the minimum amount of flux, or in other words, zero flux in this case that you can have. So again, what we, just to kind of summarize, actually I think it's the next slide, what are the things that determine this flux? Well, the larger the actual magnetic field strength for that same surface, what does that mean? More field lines per area, the larger will be the flux. So the larger is the actual surface area. So if we took an area and doubled it, you would double the amount of flux, the amount of field lines that are going through it. The larger is flux. But there's that third thing that determines the flux, and it's the orientation of the surface normal and the area. So the smaller the angle is between the surface normal and the magnetic field, the larger is the flux. So we have kind of all the parts to write down an equation, and here it is. So the magnetic flux is it's a scalar quantity. It's, you know, it's this kind of amount of field going through your area. So it's a scalar, but it depends on the magnitude of the magnetic field, the magnitude of this area vector. So what is the magnitude of an area vector? It's just the area of that surface. So here I have drawn a side view. So this blue line represents that surface, which is pointing into the page. So then the area vector is this normal here, whose magnitude is just the area. And the angle theta is the angle between the surface normal and the magnetic field. So it depends on the cosine of theta. So the way you can think about it, if this theta is 0, that's when cosine is maximum. So the flux is 1. When the theta is 90 degrees or pi over 2, cosine is 0. So that's when the flux is 0. So that's when the normal and the magnetic field are perpendicular. All right, so this is just to understand what flux is. Now let's introduce how do we write down mathematically this idea of magnetic induction. So now instead of thinking about magnetic field changing, we're thinking about magnetic flux changing. So if the amount of flux, and we use, by the way, this capital Phi for flux, going through some loop of wire changes, so it has to change. You can't just have a stationary, constant magnetic field going through your loop of wire. So if it changes, it generates what is known as the electromotive force, EMF. This might sound familiar back from 7B. We use this curly E for EMF, which is what we use for the EMF of a battery. What is the EMF of a battery? It's the voltage of a battery. So basically it's as if there's a voltage that gets generated in this wire. And if there's a voltage, we have this expression that will tell us then, well, if there's this EMF generated, then the current that will flow is going to be related to the EMF over the resistance in that wire. So basically this EMF is given by this equation, which is the rate of change of your flux. The faster it's changing, the larger will be the voltage, the more current will flow. Now this minus sign is important too, because what it tells us is that the induced voltage opposes that change in flux. So it's in the opposite direction, kind of as in the change in flux. So that's what it is mathematically, but there is, as we will see shortly, a different type of way that we're gonna actually figure out that direction. Okay, so again, for this current to be induced in our loop, flux must be changing. How can we change the flux? So remember, this was the equation we just introduced for flux. So there are 3 variables here, and you could change either one of them or multiple of them at the same time. Okay, so what is changing magnetic field? That's for B. How can we change that? Let's say we had a magnet and we moved it closer or farther away from our loop. That would change its strength. A, changing the area. That's a little bit trickier to think about, and I'll show you an example of how you can change the area of a loop. And then theta is a rotation. So an angle. So basically you could take your loop and rotate it in some magnetic field, and that would be changing that angle. Okay, so Faraday's law, which is the one that we just introduced, that tells us about how current is induced. So how is it induced? By having that change in magnetic flux. Now there's another useful law, Lenz's law, which is this method I was referring to. Instead of thinking about the minus signs and kind of doing mathematically, this helps us determine the direction of that induced current. So what did Lenz say? And here he is, lived in the 19th century. He says that the induced current is always such that the magnetic field it produces inside that wire loop opposes the change in flux. Because remember, so basically what happens is that you have an external magnetic field, it changes, it induces the current, and that induced current itself generates a magnetic field, and it's in the direction which opposes that change. So I know that's kind of a lot of words, it's a little bit abstract, so it's really helpful here to look at a couple of examples. And here they are. So this is a very busy slide, so let's kind of focus on each example at a time here. And this is the goal here really is to just practice using Lenz's law. Okay, and we'll do it by looking at examples where it's the magnetic field which is changing. So again, how do we do that? Let's say we bring a magnet closer or farther away from this loop. All right, so here, let's say we have a magnet with a north side pointing in that direction. Remember, magnetic field lines go away from the north side. And here it's just stationary. It's up and steady. Steady means it's not changing. So if it's not changing, there's no change in flux, there's no current. Nothing kind of interesting happens here. Now, let's imagine that this magnetic field, it's still pointing in that direction, but it's increasing. So let's say you take this magnet and you're slowly bringing it towards, or you could be doing it quickly. You're basically bringing it towards this loop, thus increasing the magnetic field inside the loop. So what Lenz's law tells us is that the current that will be induced will generate a magnetic field which opposes that change. So the change in flux is up, it's increasing in the upward direction. That means, so you could kind of think about it as an induced magnetic field wants to cancel that change. So if you're adding more up, the induced one will be in the opposite direction. Because again, it wants to cancel. It doesn't like that, and think about, okay, I don't like that there's more field than there was before. Let me put some field in the opposite direction and cancel that. So this is the induced magnetic field then, which is in the opposite direction. Now, how do we use that to figure out in which direction is the current? We use the first right-hand rule. So it's kind of using the first right-hand rule, but backwards here. So normally we know the current. So we, like in that picture before, there was a wire straight up, and we said, okay, let's put our thumb in the upward direction and then curl our fingers and we get the induced magnetic field. Here, think about it in this way. You're given the magnetic field, or you've just determined it using Lenz's law. You've determined that it's down. So now we use the right-hand rule to make sure fingers are pointing down inside the loop, and that will give us the current. So I actually have a little loop with me here that my son build out of his Legos for me. So I thought maybe it could help a little bit. Okay, so is my loop, and here's our magnetic field that's increasing in the upward direction. So the induced field is going to be downwards. So we use our right hand rule in such a way that my fingers have to curl down. So my thumb has to point in this direction in order for the fingers to point down in that direction. And you know, anywhere I put my thumb, it has to point in that direction. So from the top view, the current is going clockwise. So that's in this picture, this induced current going clockwise. Now, next picture here, we still have a magnetic field pointing upwards, but now it's decreasing. So imagine we have our loop. I'm holding a magnet here, but now move, and the north side is facing that way, but now moving this magnet away. So I'm decreasing the strength of the magnetic field. And remember, the magnetic field has to be oppose that change. So the change is in the downward direction as it's decreasing. It's getting, there's less and less. So you're kind of subtracting this magnetic field. There's less and less going up. So it's as if you're adding the changes downward. So the induced field will oppose that. It wants to bring that magnetic field that was, more of it was upward. So the induced one will point up. So now we want our fingers to point up when we use our first right hand rule. So in this case, when I put my thumb in that direction and curl my fingers are pointing up inside the loop. So that's, if you look from the top of the loop, is the current going counterclockwise. So that's the basic idea of applying Lenz's law. These three are very similar, except we start with a downward magnetic field here. Nothing is changing, no induced current. Here it's downward and increasing. So in this case, we're holding our magnet from above. North pole is right here, pointing this way, and we're bringing our magnet closer. So the induced current wants to oppose that change, so the induced current will be up. So that's kind of similar situation as the one right here. We curl our fingers now this way for these fingers to be pointing up in the direction of the induced magnetic field. So the current is counterclockwise. And then this situation here is analogous to that one where the magnetic field is going down and decreasing. I'm moving my north side, which is down here, away from the loop. So the induced magnetic field wants to oppose that change, so it wants to be down. So thumb has to point this way. Current is clockwise from above. So that's kind of the basic idea of applying this Lenz's law. This is mathematically how you would figure out what is the rate of change of flux. So remember, it could either be area, we're not changing area here. It could be magnetic field, we're not changing that. No, sorry, we are changing that. It could be angle, we're not changing that. So we're just left with this term, which is area. I got rid of the cosine theta term here because at least in this example, we're assuming that they're perpendicular. Or well, the loop is perpendicular to the magnetic field, or the surface normal is parallel to the magnetic field. So you just end up with a rate of change of magnetic field. All right, so this is kind of a summary of the procedure here. So first, you want to determine which direction is the flux changing. So if it's increasing up, it's changing in the upwards direction. If it's decreasing down, up, it's changing in a downward direction. And then that will tell you the direction of the induced magnetic field. It's in the opposite direction to the direction of the change in flux. So that's the first step. After that, you use your right-hand rule number 1, except instead of kind of knowing a current, you know the magnetic field. So that will help you to find the direction of the induced current, which is consistent with that induced magnetic field. All right, we'll practice more with this because it is kind of a really new concept to work with. Okay, so here is an example of a changing area. So imagine that all of this, so these are kind of represent, let's say, a train track, and these are rails, so everything is conducting. And then there's, imagine this is like a train, but there's a conducting bar here, so forms this closed conducting loop. And imagine that in here, there's a constant magnetic field which happens to be pointing out of the board. So the circle with the dot is out of the board. All right, so you could see that, so this is our area. As the strain moves, the area now changes. If the area changes, so does the flux, because let's say we start with, what is this, 1, 2, 3, 4, 5, like 10, you know, in this kind of toy model, 10 magnetic field lines coming out. As it moves, it decreases. We have 8 and less, depending on, you know, how fast it's moving and where did it go. All right. So in this case, it's the area that's changing. The magnetic field itself is staying constant. We're not changing the magnetic field, but we're changing the flux, because as the area decreases, there's less flux, less magnetic field going through that area. So you end up with this equation. Again, I'm not putting the cosine theta there because I'm assuming, as you see here, that the normal, which is sticking out of the board, is in the same direction as the magnetic field. Okay. So let's think about, let's apply Lenz's law here. In which direction is there going to be a current? Well, actually, you already see the answer here, but let's make sure we reason through this. Okay, so as the strain moves in this direction, the magnetic field is decreasing out of the page, right? Because we have our magnetic field, which is sticking out of the page, but now we have less of it. So the induced magnetic field wants to bring that back. It wants to oppose that change. So the change is into the page because we have less coming out of the page. So it's subtractive. So that means that the induced magnetic field will be out of the change. We want to bring back those field lines that we lost coming out of the page. So now we use, so we've determined induced magnetic field is out of the page. Now we have to just use our right-hand rule to determine the direction of the induced current. So in this case, you know, this is a circle, but loops don't have to be circles. It just has to be a closed loop. It could be circular, it could be rectangular, square, whatever. So in this case, we know that the induced magnetic field points in my direction. So for a right-hand rule to work, my thumb has to point in this direction, fingers curl in such a way that they point towards me inside the loop. So then my current, as I'm looking at it, is going counterclockwise. As you see, that is the case here. So there will actually be an induced current in this situation. Now, what if the train was going in the opposite direction? Well, completely opposite situation, because if it's going in the opposite direction, now we're increasing the flux because we're increasing the area. So more and more field lines are getting through that area. So that means that the change is out of the board. So the induced magnetic field has to oppose that. So the induced magnetic field is into the board. So in this case, my thumb has to point that way for my fingers to go in. So it's going to be clockwise from above. So we get the opposite result if it's the train is going this way to the right versus to the left. All right. So the last one, the last way that we can change this magnetic flux is by rotation. And that tends to be always the trickiest to visualize. So let's consider here this loop, square loop, and let's assume that its initial orientation is this way, in such a way that the surface normal is perpendicular to magnetic flux. So the green lines represent the magnetic flux or magnetic field lines. It's perpendicular, so there's no flux initial, zero flux. Now we want to rotate this loop now, so that's its axis of rotation, in such a way that the top of the loop is going into the board and the bottom of the loop is going out of the board. So imagine something like this. Here's a magnetic field, zero flux. Now we rotate it this way, and now you see, what do you notice? Now we do have flux, and that flux is going to be in the upward direction. So what does that tell us? we want the current to be in such a way that the induced magnetic field is in a downward direction because it's trying to cancel or it's trying to oppose that change in flux. So if we look from above, if the induced magnetic field is pointing down, my thumb has to, using our right hand rule, thumb has to point downwards for my fingers to curl downwards. So looking from above, the current has to be clockwise. And in this case, we use this equation to determine the rate of change of the flux. And it's a cosine. When we take derivative of that, we get the minus sign. That's where the minus sign comes from. And then d theta dt. In physics 7, in 7c, we're not gonna do too much with actually using the equations. It's mostly gonna be trying to figure out the direction of induced current and maybe, you know, some very basic analysis of magnitude. But you will have some practice problems where you will get to see how we apply this magnetic induction to problems. Okay. All right, so there's some cool applications of magnetic induction. So one I want to point out to, and again, it would have been a cool demo in the lecture that I do where I show this electric type of generator. But basically, if you ever wondered how sometimes mechanical energy can produce electricity, like if you ever seen wind power, for example, it's something rotating, or water power too. It's normally, you know, water which hits something that rotates, so it's a mechanical energy, and somehow it's an electric generator. So how does it produce electricity? How can you get mechanical energy against something that's just physically rotating and give you electricity? And it's this principle of induction which is behind it. So imagine we have this crank here, which is connected to a wire loop, and it's positioned in a location of a large magnet. So you take this crank and then you rotate it. So again, you know, of course, physically, it's not people that are generating. It's, you know, it could be wind, it could be water or other sources, but something that's making this crank rotate. And as you see what happens, as we just saw in the previous example, as it rotates in the magnetic field, in this case, the field is pointing in that direction, the flux will change, and that flux will generate a current. And it turns out actually this current will, every 180 degrees as it rotates, I'm not gonna really get into the analysis here, but as it rotates 180 degrees, the direction of that change in flux changes, so the direction of the current will change. So every cycle, it will go between going, you know, clockwise and counterclockwise. That's why you get AC, what is known as AC alternate current source, which comes out of this. So when we talked about batteries and things like that, that was always DC, direct current. The current always flew in one direction. Once you connected your circuit with a positive terminal and negative terminal, current flew from positive to negative. And this is an example of AC where the direction of the current keeps on changing. And in fact, the power that you get, or the electricity that you get in your home when you plug something in, that's an AC voltage source, because that's how electricity is typically generated. And there are other reasons for this as well. Okay, so there's an electric generator. So kind of the opposite of this is a motor. This is not really directly induction, but I just wanted to now bring an example of the opposite. How can electrical energy be turned into mechanical energy? So what is a motor? It's, you know, it's connected to a battery. There's electricity that flows, and then somehow it turns into something mechanical. It makes your wheels of your car turn, for example. So how does it do that? So in that case, there is a power source, like a battery, which is connected to a loop like this. So when you connected, there's going to be current in it. So now imagine you put this loop in an external magnetic field. In this case, in this example, the north is pointing, north side is here, south side is here, so magnetic field lines are going to be there. So here we use our second right-hand rule to figure out forces. So this has to do with Lorentz force. So the current over here is moving in that direction. That's where my thumb will point. Magnetic field is in this direction, so the force is up. So on this part of the loop, there's a force that points up. But now if we do the same right-hand rule over here on this side of the loop, now the current is flowing that way. Remember, current is the flow of positive charge, so we don't need to flip anything. Current is flowing this way. My fingers are still pointing in the direction of a magnetic field. Now we get a force that's pointing downward. So on this side, it points down. So you see there's this net torque. From one side, there's a push up. From another side, there's a push down. So that causes a rotation. So again, just this current and magnetic field causes rotation, mechanical energy. Then this is, connected to your wheels, which make them turn. So this is an example of electric motor converting electric energy to mechanical energy, and a generator converts mechanical energy into electrical energy. All right. Okay, so let's practice a little bit applying magnetic induction to various situations here. I have like 2 questions that are coming up. All right. So we have this wire, in this case it's a circle. This arrow just represents its direction of motion. It's being moved to the right in this uniform magnetic field. These circles with the necks, what do they tell us? They tell us that the magnetic field is going into the board. What is the induced current in this wire as it moves through this magnetic field, which is constant? All right, so think about this. As you're thinking about it, you should always think about the 3 things that can change: magnetic field, area, or angle. So here, is the magnetic field changing? No, the magnetic field is uniform. You're not cranking anything up. You're not moving magnets around, so it's uniform. Magnetic field is not changing. Is the area changing? No, we still have this same loop, which is moving to the right. And is the angle changing? Also no. You're not rotating this loop relative to the magnetic field. So you're just moving this loop in this uniform magnetic field. The loop is not changing. Magnetic field is not changing. No rotations. That tells us there's no induced current. So it's not enough just to have motion and magnetic field. The field or the magnetic flux has to be changing. All right. Now in this case, think about this. So here we have a wire which is carrying current, and the current is down. And now we take this wire and we pull it away from this loop. So this loop, let's say it's staying here in one place, and we take this wire and we move it away. Now the question is, what is the direction, if it's not 0, of the induced current in this loop? Okay, so again, the same thought process. Are we changing the area here? No. Are there any rotations happening? No. Are we changing the magnetic field? Well, so what do wires that carry current do? They generate magnetic fields. So right now, as this wire is sitting there, we use our first right-hand rule, put our thumb down, curl our fingers. What is the direction of magnetic field at the location of this loop? It's into the board, because my fingers point into the board. Okay, so there is a magnetic field. Now, what is moving the wire to the right do? It decreases the strength of that magnetic field. Because remember, the strength of magnetic field decreases inversely with distance away from the wire. So as this wire is being moved to the right, the strength of the magnetic field into the port decreases. So our induced magnetic field wants to oppose that change. So it wants to point into the board, because we're decreasing the magnetic field into the board. So now if we use our right hand rule, we want our fingers to point into the board. So to do that, the thumb has to point this way. As I'm looking at this loop, it has to be clockwise. So the induced induced current has to be clockwise in order for the induced magnetic field to be into the board. Now, if this wire had current going up, the opposite would happen, because then the magnetic field would be out of the board, which means as you moved it away, there would be less out of the board, induced magnetic field would be out of the board, and then you get the opposite counterclockwise current. So it's a good idea to kind of play with it. Think about what happens if you move the current towards the loop versus away, and so on. All right. So now we arrive to the kind of the very last topic, which is a good concluding point of this course. So what are electromagnetic waves? So what have we learned? We've learned just now that changing magnetic fields result in an electric field. How do they result in an electric field? Well, they result in they result in current moving, so that's actually an electric field, or their charges moving, so it's a changing electric field. Likewise, a changing electric field will create a magnetic field, because we saw that from last week when we have a current that's changing electric fields and that generates magnetic field. Now, what could be a source of that? Well, we can have a charge which is oscillating. So that's like a changing electric field. It will create an oscillatory or oscillating electric field, which in turn will then create an oscillating magnetic field, as you kind of see from these concepts that we've learned. And what are these oscillating electric and magnetic fields? That turns out that these are exactly your electromagnetic waves. So as these charges oscillate, they generate these oscillating electric and magnetic field, which turns out that then they propagate it in space, and they can do that in a vacuum. There's no medium that's required, like for mechanical waves that we learned about from the beginning of the quarter, like sound waves or water waves. EM waves do not require a medium. And what they are, they're just propagating, oscillating electric and magnetic fields. So again, they're different from matter waves. There's no medium, although they do travel slower when they do travel in a medium. And we've learned that when we studied refraction, that light slows down in different medium, which are not vacuum. In a vacuum, all electromagnetic waves travel at the same speed, which is known as the speed of light, which is given by this number, 3 × 10⁸ meters per second, pretty fast. They're transverse, which means that they travel in a direction perpendicular to those oscillations. And how they generated by these accelerating or oscillating charges. So let's look at a picture. This is how typically EM waves are depicted. Also, the oscillating electric field and the oscillating magnetic fields, they're perpendicular to each other. So you see that here's this wave structure, wave-like structure of the electric field, which is changing, and the magnetic field, which is perpendicular. But which way is the wave moving? It's moving in this direction. So let's say if the electric field is oscillating in the Y direction, magnetic field in the Z, the wave is moving in the X direction. So that's what makes it transverse, because it's perpendicular to those oscillations. And so when we talk about electromagnetic waves, what we mean is light. But light, this is kind of colloquial way of talking about it, doesn't just mean visible light. So visible light is what our human eye can detect, and it's actually a very small part of the whole electromagnetic spectrum of different wavelengths and frequencies. So as you see, it only covers about 400 nanometers of wavelength. There are waves that have a much lower frequency, like radio waves, microwaves, infrared, and then here we get to high frequency, high energy. So these are emitted by charges that are oscillating quite a lot. So they create very high energy electromagnetic waves, such as ultraviolet, X-ray, and then the highest energy ones are gamma rays. So these breakdowns are a bit arbitrary, but here they are more or less, just what defines a wave which is infrared versus gamma ray. These are these just imposed ranges of frequency that define that. Okay, another important feature of electromagnetic waves is polarization. And we talked a little bit about that when we talked about matter waves. So all waves have polarization. And what is polarization? It's the direction of the oscillation. So, you know, for example, here, and when we talk about polarization of light waves, we always focus on the electric field. So here is this, in this case, this wave is polarized in the Y direction because that's where the electric field is oscillating. So that this would be known as kind of the plane of polarization of this, you know, wave. Now, normally, if you have just some beam of light that's coming, it normally is a combination of many different electromagnetic waves combined, and each one of them has its own polarization direction. So we normally just a random beam or ray of light, which is again composed of these individual waves, is what is known as unpolarized. Why is it unpolarized? Because they don't all line up in one direction, all the polarization of the individual waves. Now, polarized light is one where all the waves have the same orientation of the electric field oscillations. So here's an example of unpolarized light. It's kind of all superimposed, and imagine this is like your polarization, direction of your polarization plane. So this one is in the Y direction, this is in the X, and so on. Now, because this polarization you can think about as a vector, you can always represent it as a superposition of your X and Y direction. You know, of course, in 3 dimensions, we would also include the Z direction. So the same way we can represent any vector lying in a 2D plane as its component in the X and the Y direction, we could do the same thing with polarization of light. Okay, so an interesting thing is that there are these materials known as polarizers that can actually take unpolarized light. So imagine here's your incident on polarized light, and again, these just represent the fact that there's a bunch of waves with random polarizations, and these are the X and the Y components. And what polarizers do is they polarize this light. So they are able to take this light and spit out light which is polarized only in one direction. So how does that happen? Well, you can kind of, as a toy model, represent these polarizers as having these vertical polymer chains. So here you see these vertical lines, and what they do is that they don't allow light to come through in that direction. So any light which is oscillating in that vertical direction will just get absorbed by these polymer chains. So what this polarizer, this particular polarizer will do, it will only allow the horizontal, all the vertical components, all the vertical polarizations will get absorbed. And what you get is this transmitted polarized light where the polarization is in the horizontal direction. So this is basically what happens when you take this incident and polarized light and put it through this polarizer. Now imagine now you take you put another polarizer. So first you put one, and what you get out is this transmitted polarized light, which is all horizontal. But now if you take another one of these polarizers and you flip it, so now these chains are facing in a horizontal direction, what do you think will happen? Well, there's only horizontal direction to be absorbed, to go through, and that will get absorbed by these polymer chains, so we get no light out. So if you take these two polarizers and you kind of make them perpendicular to each other, you get no transmitted light. And this is something that unfortunately you kind of miss out on, because in DL you actually get a bunch of polarizers and you get to play with them at home with a light source. Okay, but then there's something interesting that happens. So again, let's take a polarized light and put it through this vertically oriented polarizer, and you get this horizontal light. Now, what happens, do you think, if we now take another polarizer and orient it like this, let's say at a 45-degree angle? Well, our incident light is like this, but remember, it's a vector. We can always break this down into components, right? So if we want to now set our axis in this direction, so let's say that will be our Y, and this is our X component, we can think of this polarization direction as having some components in that direction. So the blue is along these chains, and then the green is perpendicular. So as now this light goes through, this direction gets absorbed, but anything, but the green one gets through. So basically the transmitted light is now polarized in the direction of this axis, which is again perpendicular to this polymer chain direction. So basically the interesting thing is that now if you take this polarized light and then you put these two polarizers on top of each other, you get this, this light transmitted. And now if you put a third polarizer, which has its polarization in this direction, so again horizontal, what happens now? Well, now again, let's break it down into components along the X and the Y direction. Which one gets through? The red one. So we get transmitted light, which is polarized in that direction. So kind of the interesting, cool result is that if you take these two polarizers and you orient them this way, you get nothing out. But if you now just take these two and then insert a third polarizer, which is oriented, let's say at 45-degree angle relative to these two, you will get some light transmitted. So it's kind of interesting to think of this in terms of vectors. All right, so another thing is that you can actually quantitatively figure out the relative intensity. So basically, you know, it's not that this energy disappears when it gets absorbed. The transmitted light, when it goes through a polarizer, will have less intensity. And you can, and there's this Malus's law where you can figure out the intensity of the transmitted light compared to the intensity of the incident light depends on the angle. And what is this angle? It's the angle between the polarization axis and the direction of the polarization of the incident light. So for example, if we go back here, if the light that was going through here, let's say it was only vertically polarized, then nothing would get through. Actually, that was back. When was that? Yeah, so this was, for example, here. So in this case, it was all horizontal, nothing was getting through. So what that told us is that this angle, so the polarization axis is the axis through which the light actually gets through. So that's perpendicular, so that angle would be 90 degrees. Cosine of 90 is 0, no light is getting through. Now, if it's perfectly perpendicular, that's when you get cosine of 0, and then all of the light gets through, so the intensities would be the same. And, you know, in between, it depends on their relative angles. So again, it's just, this equation just tells you what is the intensity of light that's getting through your polarizer, which depend, what fraction of basically its initial intensity. All right, and just to finish off with a couple of interesting applications of polarization, just kind of fun ones. So 3D movies basically work with this principle, and the way they work is that they're actually, what you're watching when you're watching a 3D movie is two separate movies that are superimposed. So there's two projectors here, and they're projecting the movie with a different polarization. And then these glasses that you have to wear, because you know you have to wear these glasses in order to actually get this 3D movie experience, they each one, so your right and your left eye, have two polarizers that which are in the opposite orientations. So if one projector, let's say, is giving you like this polarization in the green direction, so you're seeing that movie through the movie given by this projector through the right eye, you're seeing the movie given by this projector through the left eye, and this is what gives you that kind of 3D perception. So, you know, you can kind of play with that with your eyes when you close one eye and then close the other one, and you look at an object. When you open both of them, it's sort of this combination that gives you that ability to see things well in 3D. I'm sure you've heard of polarized sunglasses, and what they're good for is to reduce glare. And it turns out that when on polarized light, so, you know, typical source of light, you know, coming from your sun is always unpolarized. These light rays are a mixture of light from all random polarizations. But what happens when it reflects from some materials, especially things like water, that reflected light becomes polarized. So the reflection itself polarizes light, and that's what causes a glare. So very often when you look like at something like, you know, water, you get this glare. So if you, and also this polarization always is in the direction which is horizontal to the surface. So you see this is kind of a little image of unpolarized light coming to the surface, reflecting, and you only get this horizontal polarization that comes out. Now, if you wear these, if you make these glasses that only absorb that direction, right? So you want your polymers to be in that direction. So this glare, the reflected light actually gets absorbed, but then you could still see all the other polarization. So it's not like you can't see anything. You only this glare or the reflected light gets absorbed. So this, you know, this is good at reducing glare. All right, I think I'm done for today. Enjoy, and I will see you next week for a lot of review stuff.